So, welcome to this little story from Euroluna today, where I'm going to talk a little bit about vacuum chambers and how things behave in vacuum. And this is because we have recently installed a very small vacuum chamber in our laboratories. Not high vacuum, but down to at least 10 millibars or maybe 10 to the minus 2 millibars. There's a certain uncertainty there because we haven't quite got our instruments ready yet for measuring precisely where we are. We just know that we are below 10 millibar. That's the best we can do right now. Now that's 99% of the air out, and that's okay for most of the things we do. Now the first thing we did for that was taking a standard PCB. This is a test board we've had, and we put it into our vacuum chamber, gave it a certain amount of solar input, you could say, making it as though it would be in space, around 2000 watts per square meter, which is above what the solar input is in space. So we're going beyond in our testing. And that we put in our vacuum chamber and kept it for a certain while. And what we did was then to measure the mass of it on a regular basis. And I have a curve here, which maybe if you come a bit closer to it, you can actually see that we started up having this board of a mass 28.01 grams, so 28 grams and 10 milligrams. And then as I measured after a certain amount of hours, and these are in hours inside the vacuum chamber, the temperature and the vacuum made certain components evaporate from the board, and we get a curve going down in some way with a certain loss of mass. We've now done it for, as you can say, something like 250 hours or something like that. So, as I was saying about this curve, we have a decreasing curve. Of course, the mass in the PCB, this PCB, actually lowers. It's actually possible right now to see that where the lamp was very close, we have a discoloring of the surface. Nothing that matters anything on the structural component of this PCB, but there is a little discoloring there, which we've seen on other PCBs when we've had them into our oven, but typically those things happens more around 200 degrees than around the 100 or 75, which we were assuming that we were having on this board. Nevertheless, the interesting point is really that we have this curve in basic going down. We have an uncertainty band, which I'll come back to now, which we think is in the order of 20 milligrams, plus or minus 10 milligrams, let's say, on a measurement, and I'll come back to that. And the loss we are seeing over this time frame is around 0.3%, which is more or less 100 milligrams on 28 grams. So that's the expected loss from a PCB, a test PCB. Now, this, of course, was a test PCB, and the next thing we did was taking one of our solar cells, one of those that's actually supposed to fly sometimes in the future, and let me just take it. Here, this is a solar cell, mounted, of course, on a PCB. As such, it has a mass that, because of the metal and the solar cell, is higher than the PCB we had as a test. Nevertheless, it's a good and a real flight hardware that has to go somewhere. And if we take the same curve for that, I have it here. We start on the 38 grams, and then we go down to something that looks like a curve similar to the other one, though now more, you can say, more structured, and we also have some uncertainty bars on it. And the same sort of behavior is what we're seeing, plus minus 10 milligrams, something like that, a loss of around 110 milligrams in total on this, which again corresponds to something looking like 0.3% of the mass or some thereabouts. Based on this, we think that we can say that for the things that has to fly on our CubeSat, what we're going to do is that the reasonable testing before it goes in flight operation is around 1 week in a vacuum chamber, 168 hours, possibly with some thermal stress as we've been doing here, and then we know that a significant part of what can evaporate, what can outgas, will actually have been outgas before. The board afterwards may take up something again, and I'll come to that exactly now, because one of the things we discovered when we did that was that it was critical when we measured the mass of our test boards. That means how long after it came out of the vacuum chamber actually was critical, because leaving it outside the vacuum chamber, it actually took up air and water and whatever humidity there was in the ambient air and pressure over time, so that it gained weight again. And this is illustrated on this curve here, where the thing is in minutes here, but where we actually have a curve where the points were going up, and the total uncertainty here is something like 20 milligrams between this point and that point. So in a certain sense, one can have 20 milligrams of uncertainty depending on whether we measure immediately after the thing came out of the vacuum chamber or a significant number of minutes later. So that basically meant that we had to standardize on when we measure, and we measure now precisely 5 minutes after the exit from the vacuum chamber and 10 minutes after the exit of the vacuum chamber, which is what gives us this uncertainty bar here on those, so that we can say something about how much that matters from that point of view. And that's what I'm going to say about PCBs today. Thank you very much for listening.